Thanks for inviting me to give this presentation today. I'm proud to share with you how we at GE Healthcare Cardiovascular Ultrasound are leveraging digital twin technologies. So my name is Krissy McLeod. I'm digital manager in cardiovascular ultrasound. And I just wanted to start first by giving a bit of context into what we're developing in the cardiovascular ultrasound group. So we are the creators of the Vivid range. And the Vivid range covers our high-end Vivid E-series scanners. So these are with our the best computing resources and thus the best image quality. And then we have our Vivid S series as our mid-range product, our Vivid T series as our affordable product, and then our Vivid IQ as the portable laptop version of our scanner. So in addition, we develop our EchoPack software, which is the software that enables users to evaluate the exams offline on a PC. So to give a bit more of a flashy intro to what we develop on our scanners, I thought I'd utilize the recent marketing video from our latest Vivid release. So this is the Ultra Edition, where they summarize what we're working on and why we're developing the features we are. So I might actually need to, let me unshare and reshare so that I can get the audio as well. Let's see here. So include sound. Pablo, could you just confirm you can see my screen once again?
I can see it.
Great. Okay, here we go. So that was kind of a nice summary of what we've just been working on in our previous release. And so I just wanted to mention that ultrasound is the go-to imaging modality for cardiology. So as of today, more than 100 million exams are performed each year. And the reason for that is that ultrasound is portable. So it's easy to move the system from one patient room to another or from different areas of the hospital. It's also not requiring any radiation, so it's safe to use on all patients. It's also has the capabilities of measuring blood flow and other important cardiac phenomena, which kind of makes it a one-stop shop for analysis of the heart, also in children. And it has the advantage, thanks to its portability, of being able to be wheeled into an operating room to support both interventions and surgeries. So I've myself seen one of our E95 scanners being wheeled into an operating room after open heart surgery to verify that the blood flow was indeed closed as planned during the operation. So ultrasound is kind of a widely used tool these days, and thus very relevant for in silico cardiology. So where do we traditionally fit into this digital twin puzzle? So let's just look back at this nice diagram put together by the group. So the point of the puzzle where this all starts is with the clinical data itself. We're of course dealing with medical images and cardiovascular ultrasound. We are typically using more statistical models, so driven by the data that we have at hand, so our imaging data. We do also work with some mechanistic models, so I'll talk briefly about that afterwards. So this is kind of where we have so far been fitting into this whole framework. And I wanted to talk a little bit about how we're moving beyond this traditional paradigm. So we are starting on our side at GE by building more advanced digital twin relevant technologies. So that's activities that we've been working on, and I'll briefly go through some of the ones that we've released in our latest Ultra edition. We're working towards sharing more tools, and this is to open up the opportunities for external collaboration. And we're also now partnering more actively with hospitals, universities, and other companies so that we can work together to bring more advanced functionality on our systems, which are already available around the world in our large install base. So let's first look at some of the digital twin relevant technologies we've been building internally at GE. So these kind of technologies we've been working on in order to kind of build the full picture of an echocardiography exam. So we're talking about the acquisition itself of the images, the analysis of the images and how we visualize those images, of course, the measurements that are used in order to drive diagnosis, and also the reporting that's used to support the clinical care pathways long term. So in addition to looking at kind of each of these aspects individually, we're also working towards how we can streamline the whole echocardiography exam workflow to make the exam process more efficient for users. So currently 90% of sonographers suffer from musculoskeletal disorders due to repeated strain on especially on the wrists and so on. So reducing the total exam time is both in order to enable more patients to be analyzed, enabling more advanced analysis techniques that typically users wouldn't have had time to carry out, and also just to minimize the strain on the sonographers and cardiologists themselves. So let's take a look at some of our exciting new digital twin relevant features that we're coming with in our Ultra edition. So we have advanced imaging of the blood flow using blood speckle imaging. So here you can see, thanks to these nice visualization techniques, the flow of the blood through the different chambers, and of course highlighting when there is turbulence or other problems within the blood flow within the heart. And so this type of work has been developed recently, leveraging more the statistical models side of the digital twin puzzle, so using pattern recognition and advanced imaging in order to enable this type of analysis. Then when we're looking at how to visualize and analyze the images, so one example is our Auto TVQ package, which is the tool to automatically quantify the tricuspid valve. So here is showing the workflow on our system in our latest edition. So it's enabling an analysis of the valve itself, and by doing so, the user is able to measure the valve annulus and quantify the status of the valve. So this type of technique is leveraging more mechanistic style models. And as you can see, this type of tool requiring input from the user to place these landmarks, these type of solutions could be automated thanks to statistical models. So that's kind of where we see these workflows going in the future, is to automate this pipeline so that the user saves time in kind of correcting these points and these different angles of the plane. Now, when we think about measurements in the heart, one example is from our latest edition is the automatic measurements that we're now performing using in the left ventricle of the heart, leveraging AI technologies. So you should recognize the first author of this paper. So this is the work from Andy, who was the previous presenter. They're leveraging the statistical models piece of the digital twin puzzle. Similarly, as I mentioned, we're working on speeding up the examination workflow in order to make it more efficient. So one way that we're doing this is, for example, with our Doppler images, automating the analysis of the Doppler spectrum so that we can invoke our existing automatic measurements. So the user goes straight from acquiring the image to hitting our measure button and having the full measurements performed automatically thanks to the detection from the system of which measurement to perform, and then our automatic measurement package running sequentially on top of that. So here you see a few examples of how that kind of workflow is very efficient for users and enables to speed up the examination time quite significantly. So this was also algorithms that were leveraging the statistical models. And again, you should recognize the first author of this paper. This was work from Andy to leverage AI technologies in order to perform this automation of the analysis of the type of measurement to perform. So now that was kind of a sneak peek into the kind of digital twins technologies that we have on our system today. As I mentioned, we're working actively towards sharing our data access more actively with third parties, be it other companies and academic groups, universities, and so on. And just to give an example of this type of approach, if we consider 3D echocardiography in particular is both clinically relevant and also technologically interesting when we're thinking about academic sites and writing technical journal articles. So, for example, the number of publications where 3D echocardiography was a keyword is significantly increasing over the past years. So just last year, there was more than 600 publications on 3D echocardiography. And this is also supported by the clinical guidelines that are now recommending the use of 3D echocardiography in clinical practice. So the state of the art as of today has been to use 2D imaging. And of course, we all know that analyzing a 3D object in 2D is removing some of the important information. So it's just natural that more analysis in 3D is required in order to kind of fully capture the picture of the heart. So the reason why this has been a challenge so far is due to interoperability. So in echocardiography, this is complex since images are stored in raw data format. So this is necessary in order to maintain the highest possible quality of the data. So these are very large image data sets. So when a raw image is actually transferred to the PIC system, so the image archiving system in the hospital, it's converted to DICOM, which is a standard format, so that it can be opened by any workstation. The challenge is that this 3D conversion from raw to standard DICOM, it causes the loss of this third dimension. So it's not very useful to image in 3D if you lose the third dimension. So what it kind of works, how it kind of works is that the acquisition takes this raw format, and this is using private DICOM tags, so that the information is stored within tags that cannot be opened by third parties. Only the vendors have access to their own their own 3D data formats. So when the conversion occurs from raw data to DICOM, as you can see, it just takes more or less a screenshot of what you saw at the time of making that conversion. So when it comes to performing analysis on an external workstation, you cannot do any kind of 3D measurements because you've lost this third dimension. So this is what motivated the Open4D initiative, which is led by us at GE. And this is to create open readers so that anyone in the marketplace can access this 3D data. So it means also from the Siemens and Canon and Philips data in addition to our own system. So we all suffer from this same issue with our 3D data, that we need our own 3D data readers. So now with this Open4D initiative, creates the readers so that users are able to transfer this 3D data to their PIC system and analyze it in full 3D as though they had the vendor software itself. And this means that it's now possible to open a 3D image data format in any workstation. So it could be in the GE workstation or any other workstation, or third-party solutions for data visualization. So this is kind of opening up the 3D ultrasound market to other users outside of the main imaging vendors. So, and this initiative to share these kind of readers, this is what we believe is enabling exciting cutting edge technologies. So the kind of digital twin technologies that we may not have time to work on ourselves internally. So now we can share the data coming from our systems using this Open4D platform and perform third-party processing of that data. So some examples of what others have been working on so far was, for example, 3D printing of the valves. So this is the kind of output that you could get, for example, from our auto TVQ algorithm that I mentioned previously, that's automatically analyzing and segmenting the valve itself. So by 3D printing the valves, it's possible to then support the planning for interventions, valve replacement, and so on. Some other solutions that third parties have been working on is related to virtual reality. So, for example, here, creating a headset to control and manipulate the view of the valve. And also, of course, some groups are working now on augmented reality solutions. So this is, for example, using HoloLens technology to navigate through the data generated from our systems and then adding in these layers of additional information. So all of these kind of technologies are now possible for third parties to develop, now that they can access the data readers. And that's not just on our systems, it's also, as I mentioned, on the other main imaging vendors as well. So this really opens up the market for sharing this kind of possibilities with third parties as well. So then the next step that we're working on is more towards active partnering with third parties. So we're working together with some key third parties already to bring more digital twin technologies to patients. And the way we're doing this is through our developer partnership program. So this program is where we've kind of made a strategic choice to move us to the side a bit and open up the space for third parties to develop solutions that can be deployed directly on our scanners. So not just the solution where you would download the data from the scanners and then analyze it in additional software. So this is the type of partnership that we envisage where users can actually deploy their apps seamlessly on our system, so both on our scanners and on our workstation. And this type of active partnership, we see it as kind of a win-win, enabling more third parties to reach the market. We have the install base that enables these kind of solutions to reach many more customers. And on the flip side, by partnering with third parties, it enables more functionality to come to our customers through this marketplace solution. So the way we do this from a technical perspective is by developing software development toolkits, and the access to these SDKs is to kind of kickstart the development for third parties. They have full support on Windows platforms, which is where we develop such solutions ourselves. And the beauty of these SDKs is that it's leveraging the APIs that we use ourselves internally for our own app developments. And so that means that the support is available because it's the same APIs that we need to develop and maintain ourselves internally. Access is very easy through an open GitHub repository, and we provide our latest releases, test tools, data, documentation, and issue trackers. So it's possible to send requests to the team. And it's also possible to stay up to date with the latest products that we're releasing, pre-releases, and anything that would be relevant for third-party app developers. As I mentioned, this is the same kind of framework that we use for our own internal apps. So for example, showing here a few of our apps that we have deployed on our systems already. And so with this initiative, we now enable third parties to distribute their apps through our marketplace. So this is powered by Edison, and users are able to download the apps directly from the marketplace and can have these apps installed on their systems using the same mechanisms that we would for our own internal apps, and the same interface and same SDK. So the apps can essentially look very similar to our own internally developed apps. So making it easier for users to have kind of a consistent user interface when they're dealing with apps, be it from GE or from third parties. So that was kind of my short introduction into how we're working at GE Cardiovascular Ultrasound to build more digital twin technologies. And I'd like to kind of leave you with the message to think about how we can build this story together. So we're working ourselves internally to build more technologies in this space. We're continuing to work towards sharing more of these technologies with third parties. So opening up the market for small startups or for academic groups to develop solutions that can be deployed on our system. And then offering this marketplace that allows third parties to also sell their apps that they deliver through our marketplace. They reach all of the same customers that we reach. So that opens up kind of a huge marketplace for small companies that don't already have this kind of established marketplace themselves. So that was all I had to share with you today. So I'd like to thank everyone for your attention and joining this great winter workshop. And I believe we have time to take some questions, if anyone has any.
Thank you very much, Krissy. And thanks for taking the time. Audience, your chance to engage. Questions, curiosities, comments. Raise your hand. Joao, go.
Hello, Krissy. How do you do? I was going to send you an email, but like this is much faster. How is easy to, or is it possible to get access to this for with the 3D viewer that we can use for every machine, or not really? The one you were speaking like in the middle, more or less.
It's very easy to get access. So if you just send me an email, I can arrange that.
I still have to send an email. Okay, perfect. Yeah. No, thank you anyway. Super cool presentation. I am very happy with the way you are doing the things nowadays with this platform for a third party. I think it's very cool.
Thanks.
Cameron.
Yeah, the main reason we need your email is just so that we can get your GitHub credentials in order to add you. Yeah.
Yeah, perfect. Thank you.
Great. Cameron.
Yeah, hi. I had a question about the blood speckle imaging that you've got on the screen there. On your slide, you had the paper that I think is actually in pediatrics. And my colleague and I were playing around at the end of last week with the pediatric probe and trying to do some speckle imaging on my heart, and it didn't really work that well using a pediatric probe in an adult, obviously. And I was just wondering whether this blood speckle imaging is coming to adults, or if that's something that might be around in the future.
So indeed, we prioritized deployment in pediatrics first, since that's the area where analyzing the blood flow is most critical. It is not so easy to get, in general, good imaging on an adult with a pediatric probe. So it's not ideal to try and use the probe on yourself. But there's nothing limiting the technology. It's just a matter of tweaking the parameters so that it's suitable for the different probes. So it is planned that we would extend this type of imaging to adults as well.
That sounds great. Thank you.
I've also tried on myself to get a nice image, and it also doesn't work very well. The pediatric probes are specialized for small children, so.
Great. More questions, audience? I have a question, Krissy. I'm really curious to know how these alliances work when you want to deploy your application. I'm especially worried about or intrigued about how you go through the regulatory loop. You have a third vendor approaching with a solution, and then do you take on board all the approvals and all the processes in-house in GE, and there's a kind of prioritization and selection of who goes into that process, or is a kind of you take a consultancy role and you assist the third party to go through that loop, or how does it work? Because having an app available for clinical use is not only an engineering plugin, it's also the approval of the regulatory service.
Yeah, good question. It's indeed a big chunk of the work to approve devices for medical use. So the plan with the third-party initiative is that the third parties are responsible for their full solution. That includes also the regulatory paths. So under that arrangement that we have with this developer partnership program, we've covered the regulatory support needed to be the host of apps, but we do not file the regulatory support for the apps themselves. So we do have other arrangements with some partners where we would take on the regulatory aspects, but it wouldn't be under exactly that same framework. Yep. So the advantage of the developer partnership program is that the users are full owners of their solutions. They can upgrade and make changes if they want to. And since that is completely developed independently, it's much harder for us to take ownership of the regulatory process, because it requires quite a lot of information about the solution and the testing process and so on. And this is something that makes more sense for the developer to manage on their side.
Yeah, makes sense.
But we do kind of work in many different mechanisms for collaboration. So also with universities and clinical partners that don't have the resources to develop and follow up all of these additional processes, then we work together in using other mechanisms.